Okay, so I hope that this is the last video you'll have to watch. It should be. I anticipate I'll be able to fully join you without pain medication causing me problems in my speech. After today's class, we'll have a couple saplings you should be able to do. Sapling number 17 is a finishing up of the kinetics chapter, and 18 is kind of the introductory questions from your chemical equilibria chapter. A little word about this video that you're going to watch. This one is really not designed for those of you who are joining me in class, but it is designed for those who haven't considered what the importance is of class time. They haven't put that as an important part of their learning, and I just wanted to explain why I feel it is a valuable resource. So the rest of you will just have to endure it because it does have some questions associated with it there. And then we're just continuing on with lessons dealing with chemical equilibria. Now, with today's class, it's just going to be a whole series of multiple choice questions. And what I want you to do is, after I present the question, is to pause it, look through your notes, and see if you can figure out the right answer. Do your very best to see if you can find it, and then rejoin the lesson and see if you got it right. What I will do is tell you what the right answer is and then spend a little time explaining why that's the right answer. So if you got it right and you understand why it's right, you can skip ahead to the next question, or if you need to, you can watch my explanation. So it may be a lengthy lesson for you, depending upon how much of my explanation you need to watch. But remember, you can always stop if you get tired of listening to me and come back a little bit later. Okay, so here's our first question. It has a mechanism. Now, this is drawn from an old exam question. And we have our mechanism. It's a two-step mechanism. And I just want you to find, first of all, what NO2 is. So that's our first one. What is NO2? Is it a catalyst, a product, a reactant, or a reaction intermediate? Pause, think about it, and rejoin. Well, NO2 is a catalyst. How do I know it's a catalyst? I know it's a catalyst because it is applied as a substance that later gets regenerated. So if you see it in an early step on the reactant side and then later as a product, then that is a catalyst. Catalysts get consumed or get used in a chemical reaction, but not consumed overall. Because you could see in the overall reaction, they would go away, okay, and would not be included if I were to sum up these two reactions. Okay, now I want you to look at NO. Okay, pause the video and think about which substance or which category it would fit in. Well, NO is a reaction intermediate. An intermediate gets produced and later consumed. So it's there in the interim. It appears and then goes away. Again, it gets canceled if you were considering the overall reaction. So what is the overall reaction? It would be SO2 reacting with oxygen to produce SO3. Notice that neither the catalyst of NO2 that you have to put in, you're putting that in as a chemist, making this reaction happen faster. But when it's over, it's still there. It hasn't been overall consumed. And the NO is not in that overall reaction because it gets produced and then goes away. Our next question here. Again, we have a chemical, we have a, what's the word I'm looking for? We have a mechanism, okay? It's a three-step mechanism. First step is fast, then a slow step, then a fast step, okay? We know that the slow step is what we call the rate determining step because it determines the rate of the overall reaction. What I want you to do is determine the rate law for this reaction. Now, this should have taken you quite a bit of time, and the correct answer for this is D. Now what I'm going to do is go back and forth between a couple slides to explain how it's D, but let's start by writing the rate law for the slow step. The rate law, rate, is equal to K, and then you look at the reactants only and raise them to the power of their coefficients. So it'd be Cl and CHCl3. So that doesn't match D, does it? It has an issue, and the issue is that Cl is not a reactant in the overall reaction. It's good if you take a mechanism and you write the overall reaction, okay? We've got a couple chlorines on the left. We have a couple chlorines, the atom chlorine on the right. Those cancel. We have, what else is canceling? CCl3 is canceling. And that gives us the overall reaction, which I'll write down here at the bottom, of Cl2 reacting with CHCl3 to produce HCl and CCl4. So Cl2 is not a reactant, and we cannot leave a mechanism with that. So we have to do a substitution. To do a substitution, you will utilize this fast equilibrium that is above it, okay? So on the next slide, I want to write to do is find a substitution for this intermediate that we're not allowed to leave in that rate law. So what I'm going to, so where I saw the Cl, I am going to put in the substitution. Rate is equal to K times the other K, which is still a constant, and I'll just continue to call it K. And instead of the Cl, okay, remember we had the Cl2 to the 1/2 power. And then that's times CHCl3. Now, a lot of times students will ask, how did I get this K? Remember, we have that K, combining it with this K, a constant times a constant is still a constant. So all those K's get combined together to give me that. Now this is now a good rate law. And that is why the answer is D. Now I don't have them in the same order as it's written here, but it's the same thing. Equilibrium. Cl2 in equilibrium with 2Cl. We are going to come up with a substitution for the Cl using this. We know that it's an equilibrium, and the rate of the forward reaction is equal to the rate of the reverse reaction when you're at equilibrium. We'll learn more about that in the next chapter, or you started to learn about it as we watched those videos. So the rate of the forward reaction is rate is equal to K, and I'm going to call this Kf for forward, times Cl2, and the rate of the reverse reaction, and let's put a little r there, is equal to the K of that reverse reaction times Cl, but we're squaring it, so we're considering the reaction in reverse. Now, if it's at equilibrium, then the rate of the forward reaction has to be equal to the rate of the reverse reaction. So Kf times Cl2 is equal to Kr times Cl, and that's squared. Now, what we're trying is I'm going to solve for just Cl. So let's get our constants over. Kf over Kr times Cl2 is equal to Cl squared. And then let's take the square root of both sides. Okay? Now, if you take a constant divided by a constant and take the square root of it, it just gives you a constant. So I'll call that K. And then it would be Cl2 to the 1/2 power. That's what a square root is. If you take the square root of something that's squared, then it's just Cl. So now we've got something to substitute in. Okay, we're going to take this and substitute it in for the Cl. We have a K here. Maybe I ought to call it a different K. K. Your next thing to consider is this one. Again, this is an old exam question. And I want you to just look through that and circle which one of those words at box 1 and box 2 give you the correct answer. So it is a heterogeneous because what we have is a nickel solid surface here with gases coming in and attaching to it. That is an example of a heterogeneous catalyst. And the second part is lowering, and that's always how a catalyst works. The activation energy is the mountain that has to be climbed of energy between the reactants and the products. And catalyst always works by lowering that mountain. So it's a lowering of the activation energy. Now we're ready to look at chemical equilibria. So we're leaving kinetics and looking at equilibria. And the first one is just writing the correct equilibrium constant expression. Now you will see this sometimes called the law of mass action. I rarely call it that. But if you're looking through old books and you see that, they're talking about this expression. So pause and select the right answer. Okay, so the right answer is B. It is products over reactants raised to the power of their coefficients. That plus sign doesn't get included. They are multiplied here. That's a times, not a plus. So that is the correct answer for that. Now, K tells you something about the equilibrium. It tells you once equilibrium is established whether you have more products or more reactants. So I want you to select the one that shows that you have much more reactants than you have products. And this is, don't ignore what's below, okay? You're just considering what's above right now. Now, if you have much more reactants and you have products, then you have a very small k. Because remember, k is equal to products over reactants raised to the power of your coefficients, whatever they may be, okay? So if this is a very, very small number, then the denominator is large, and you have a whole lot more reactants. Anytime k is tiny, smaller than 1, a fraction, that means you've got more reactants. Anytime K is larger than 1, then you have more products. Now that range between negative, 0.1 to 10, that's going to be fairly equal, not exactly equal, but fairly equal amounts of products and reactants. Okay, now I want to consider this bottom part. Which of the above of these guys up here, and let me erase everything to let you be able to see it well, which of those can never be a value for K for any possible reaction? Well, the answer is C. Why? C is a negative value. You can never have a negative value of K. K is products concentration, and I probably ought to put square brackets around that. Products concentrations can't be negative. You either have none or you have some. So K can never be negative. You can have negative powers of those powers of 10, but you cannot have a negative value of K. Okay, now this is probably one of the most missed concepts. It's not a difficult concept at all, but it's missed because it is unexpected. Students don't expect this to work this way. And so I want you to consider these two reactions that you see here, okay, and use them to come up with a K for the reaction below. The answer is B. And if I could tell what you all answered, I would guess that a lot of you did not answer B because this is so commonly missed. So let me explain how it is. If I'm going to construct this bottom reaction from those reactions up there, I need to reverse the top reaction. So I'm going to go ahead and write it reversed. That would be D producing 2A plus B. When you reverse the reaction, you take 1 over that value. A lot of times students will make it negative. Why will they make it negative? Simply because that's what we did with delta H's, okay? With delta H, and now we learned this first, and so it's easy for us to want to apply those rules. When you reverse the reaction, you change the sign. But with K, since it's products over reactants, if you reverse the reaction, you're taking the reciprocal. And so that is equal to 4. Now the second reaction I'm not changing, okay? C going to D. And so its K value is 575. Now let's see. We've got to add these two reactions together. And we can cancel the D. And that will leave me with C going to 2A plus B. These two reactions, 1 and 2, add up to give me the reaction we're looking for. So then what do we do with our K's? And here is the second place that students mess up, okay? You don't add them together. Now, adding together is what you did with delta H's, but you multiply them. So I would recommend you go and review your notes to see why, because if you can understand why, it's so much easier to remember that you don't add them. Again, with delta H, you would have added them. That's the rules for energy. But energy is not what K is, and so you multiply them. Now, the process is not hard. Like I said, when you reverse the reaction, you take the reciprocal. That's what we did here. When you add reactions, you multiply their K's. None of that is difficult, but this is missed over and over again by students because it's not hard to do, it's just hard to accept. Now, in this one, this was an old test question again, and I'm going to put the right kind of arrows in here. That was the only kind of arrow we had for the world of writing tests in this program. But this was an old exam question. I didn't like the way it was written, so I added this statement up here at the top. So we're going to start with only NO. Okay, and we know that this reaction will proceed to the left to produce some N2 and some O2 as it proceeds, okay? And we have a K value here. We notice that it's a very small K. With that, select the correct answer. Now the answer for this one is B. The concentration of N2 is equal to the concentration of O2. Why would that be? The reason for that is as it proceeds to start producing some of the reactants, because you're starting with pure of this, every time it makes one of the N2, it has to make one of the O2. So those must be equal to each other. Now, why are the other ones false? Let's start at the bottom. When you are a chemical equilibrium, the reaction never stops. So that's why D is wrong. It is still reacting. It is just that the forward reaction and reverse reaction are happening at the same rate. Okay? C, the concentrations keep changing. No. Once you've achieved equilibrium, the concentrations are not going to change. A says that the concentration of NO is equal to the sum of the concentration of the other two guys. Well, that is not true. How much is in there at equilibrium has nothing to do with those coefficients. And so that's kind of playing on that 2 there. It has everything to do with this. What we know is that at equilibrium, the concentration of NO is far greater, and I'll write it this way. The concentration of NO is much, much greater then the concentration, no, I'm sorry, is small, very tiny, is much, much less than either the concentration of N2 or the concentration of O2, okay? Because of the value of K, we know that there are way more products than there are reactants. That is what a very small K will tell you. Okay, now let's see if we've got it. Here's the answer. So you can keep on working until you get that answer. If you get that answer, you've got it. If you can't get that answer, rejoin me and I'll show you how the answer is 8.9. Okay, so we're trying to produce this reaction from those pieces. It has SO2 on the left. The top reaction has SO2 in it, but it's on the right, so I have to flip the reaction. That gives me SO2 plus 1/2 O2 producing SO3. Now, when you flip the reaction, you take 1 over the K, 0.45. This will give you the Kp for this reaction. All right, so that gives me the SO2 in place. It also gets me the SO3 in place. For the second reaction, I again have to take the reciprocal of this reaction. Flip the reaction. So this puts the NO2 on the left. It puts the NO and the 1/2 O2 on the right. And if you reverse the reaction, you take 1 over that value. Now the 1/2 O2s are going to cancel to give you what you were looking for. You were looking for SO2 plus NO2 gives you SO3 plus NO. If these two reactions add together to give you this overall reaction that you see right here, then your K's are multiplied, okay? So take the reciprocal and then multiply them, and that is what gives you that answer. All right, so now you're ready to do saplings 17 and 18. 17 is finishing up the kinetics chapter. 18 is dealing with these chemical kinetics concepts. I will be joining you in office hours on Monday. I'll make sure I'm not taking pain medication so I can clearly think. I will be there between the hours of 1 to 4. We'll be keeping an eye on Piazza whenever I can throughout the weekend to help you as you're working on your sapling. And for any problems that you're still struggling with or any concepts about anything we covered this week, please join me in office hours and I will be happy to help you.